Okay, we are getting started, and welcome to our first Thinking Beyond of the fall 2025 semester. Before we get started, for anyone new, I'll just give my usual announcements, and that if you have any questions during tonight's talk, you can submit them using the chat feature at the bottom of your screen, and we'll get to those at the end of the hour. And we are recording this, and we will post it online if you want to rewatch or share it with friends who are interested. And then my last announcement is just that next month, our Thinking Beyond webinar is September 29th, and it is with Phil T on the threats and promise of AI. So I will send out the registration links about mid-September, so look out for those. And I will just turn this over now to the moderator for tonight, Beyond Center Deputy Director, Sara Walker.
Hello, everyone. Thank you for joining us this evening. I'm very excited to introduce our speaker for the evening, Dr. Wutte, especially since she is our inaugural Bros Fellow in the Beyond Center. And so we had a fabulous lecture from her a few months ago on a related topic about the nature of time. Dr. Wutte is a theoretical physicist working at the interface of gravitational theory and quantum physics with special application to the properties of black holes. She obtained her PhD from the Technical University of Vienna in Austria and is currently a postdoctoral researcher in the Beyond Center. She's going to give us a brief taster on the nature of time and Einstein's theory of gravity and how it connects to some of her work. I'm really excited. Thanks so much for being here tonight.
Thank you so much, Sarah and Paul and Jessica for having me here. I'm super excited to be here. I will start sharing my screen now. So I hope you can all see my screen. So what I want to talk about today is time. And I want to approach this topic from Einstein's theory of gravity. So his theory of general relativity. So I think time is a super interesting concept because time is somehow something we talk about in every day. So we talk about in our everyday life. Somehow we have a quite negative relationship to it because we often say that time's always running out, or we never have enough time in our days and in our lives. However, the notion of time in physics, as we understand it in modern day physics, does not fully coincide with our intuitions that we have from our everyday life. And I kind of want to explain in this talk what are the consequences for time in Einstein's theory of special and general relativity. Now, to understand time, it is useful to kind of look back and to kind of see what was the perspective of on time throughout history. And one could start the story in many places. But one good point to start it is with Newton. So Newton is by some people regarded as one of the, or perhaps even one of the best physicists of all time. And in 1687, he published his book, Philosophiae Naturalis Principia Mathematica, in which he described the laws of motion. And in this book, he needed kind of a setup where his forces could act. And he introduced the concepts of absolute space and time. And here the key idea was that time and space are absolute and they are the same for any observer. So the way to think about this is that time and space are like a backdrop and this is fixed. And let me kind of stress what this means. So in Newton's physics, time is absolute. So it's independent of location and motion. And space is absolute in the sense that everyone agrees on distances and positions. However, velocities are relative in the sense that they will depend on the observer. And you can think about this we can visualize this with an example. So for instance, let's imagine we have a train which is moving at 50 miles per hour relative to the ground. However, if you're a passenger sitting on the train, it will move at 0 miles per hour relative to you. And so the way to think about space and time in Newtonian physics, I draw here a pictorial representation of this, where here we just have a two-dimensional space instead of our usual 3 dimensions for visualization purposes. So here space is the set of simultaneous events, and the time is the same at each point in space. And this way of thinking about time and space was for a long time regarded as the absolute truth. In fact, around the 1800s, it was believed by many people that physics was kind of at the end, and that the major discoveries were already done. However, this couldn't have been further from the truth. So at the beginning of the 1800s, it was realized that light had exhibited behavior which are typical for waves. In particular, it was realized that light showed interference. And what interference is, it can be, you can explain this with water waves, because these also exhibit interference. So let's imagine you're on a boat, and this boat is being rocked by waves, and sometimes the waves combine in such a way that the boat rocks more forcefully, and sometimes they will can't just exactly cancel each other out so that you're at rest. Here we talk about positive and negative interference. And it was realized that light also has this behavior of interference. Now, one had these experiments that all showed that light behaves as a wave, and it was very natural to think at this point in time that light would need a medium to propagate through our universe. And the reason why this was very natural was because also the other waves, which were known at the time, needed the medium. So in water waves, you have them in water, and sound needs the air to propagate. And so what people postulated at this point in history was a medium, the so-called aether, through which the light travels from the sun to the earth. So light reaches us through this medium, which is the aether. And so people thought this aether had to exist. And the natural thing to set up was to set up an experiment to measure this aether. And in 1887, there a famous experiment took place, the so-called Michelson and Morley experiment, which tried to measure this aether. And Michelson was at this point in history regarded as one of the experimentalists at that time. I mean, he was extremely famous. He conducted this experiment with his friend Morley in 1887 at the place which is now Case Western University. And what they did was to set up an experiment to measure the speed of the Earth through the aether. And what they did was they compared the speed of light in different directions. However, no matter how they measured it, they always measured the same speed of light, no matter if you were kind of going with the aether wind or against it. And this led to the aether model being eventually discarded. So Michelson was actually extremely haunted by this experiment, so he continued to try to measure the aether throughout his life, because he thought that this had to exist, and he performed the measurement with ever-increasing precision. However, he just always found the same speed of light, completely independent of motion. So while he regarded this experiment as a failed experiment, this constancy of the speed of light would actually be an extremely crucial ingredient for a new theory that was developed in 1905 by Albert Einstein. So in 1905, Albert Einstein published his theory of special relativity. And at this point in time, he was extremely young. He was 26. And what is actually also very interesting is that he was not working at the university, but he was actually working at a Swiss patent office when he published his paper. And this paper was very soberly called On the Electrodynamics of Moving Bodies, somehow not suggesting how groundbreaking these ideas were. And in his paper, he introduced two principles. The first principle is that the laws of physics are the same for any observer which does not accelerate. So this is the principle of relativity. And the second principle was the principle of the constancy of the speed of light, which states that the speed of light in vacuum is the same for everyone, regardless of how fast you're moving. And the theory, which is based on these two principles, is today known as special relativity. Now, the first principle is not the surprising principle, because this is the same as in Newton's theory. However, the second principle was really the surprising thing, namely because here you keep the speed of light fixed regardless of any motion. But now that you put in this new ingredient, namely that the speed of light is fixed for everyone, something has to give. And the shocking thing, so to speak, is that what gives is space and time. So an immediate consequence of this special theory of relativity was that Newton's absolute space and absolute time had to be replaced by an entity, which is space-time, and they have to be treated together, and they cannot just be separate. They cannot be treated completely separate from another anymore. This was very surprising. And there are quite drastic consequences of this. So since here in this talk, we're talking about time, one might wonder, what does this change for our understanding of time? And it actually changes quite a lot. Namely, moving clocks tick more slowly compared to someone at rest. And this is an effect which is called time dilation. And furthermore, the elapsed time will depend on how fast you're going. However, this effect is relative, so the observer will see the moving of you will see the moving observer, which is moving relative to you. You will see his clock ticking more slowly. But it's not the only thing. Also, simultaneity is not absolute, but it's something relative. So two observers in motion will not agree on whether two events happen at the same time. And this can be exemplified with a famous Gedanken experiment, which is called Einstein's train, where you have an observer which is located between two trees. And these are hit by lightning simultaneously from his perspective. However, you have another observer, the observer B, which is on a moving train, which is moving close to the speed of light. And that observer B will not observe the two events as happening simultaneously, but for him, the front tree will be struck by lightning earlier than the back tree. So you have all of these weird effects that happen due to special relativity. And in fact, one kind of has to abandon the talking about one time at all, because there are many times. So every observer has their own time, and my time will be different from your time if one of us is moving. So there are all these effects that take place. Now, you might wonder, like, why don't we talk about one time on Earth? And the reason why we can still talk about a time, like for instance today, this talk is at 6 p.m. MST. The reason why we can all agree on this time is because these time differences are tiny on Earth. So all of these effects, these special relativity effects, become only relevant when you're moving close to the speed of light, so at very high velocities. So these are all already very interesting consequences, but Einstein actually realized that this was not the only necessary development that had to occur. And the reason, and the way he realized that there was more to do was when he started to think about how gravity fits into all of this. And here I want to read a quote to you from his autobiographical notes. So he said that the special theory of relativity is only the first step of a necessary development became completely clear to me only in my efforts to represent gravitation in the framework of this theory. So as soon as he started to think about gravitation, he realized that there was more to do. And in fact, in 1907, so this was just 2 years after he had published his theory of special relativity, he had an important thought, a thought that he would actually later call his most fortunate thought. And something interesting about this is that at the time, so in 1907, when he was just 28 years old now, he was actually still working as a patent clerk. So it took some time for his ideas to be accepted because they were so new. So his most fortunate thought went as follows. So he was imagining that he was in an elevator, and at some point the rope that held the elevator got caught, and the elevator was freely falling. And now, when you're freely falling, what you realize is that you feel weightless. So you feel like as if no forces are acting on you, and any objects that were with you in the elevator, so here in this picture, for instance, a ball, they also are just floating next to you. And this kind of Gedankenexperiment that Einstein thought up made him realize that an object in free fall does not experience gravitational forces. So if you're in free fall, it is as if you were actually just being weightless. So being in free fall is like floating in space. So this kind of thinking led him to develop a new theory. And this is what is referred to as Einstein's general relativity, which he published in 1915. So here you can see, I mean, from this most fortunate thought in 1907 to 1915, there were 8 years, so it took quite some while for the mathematical backbone to be developed to describe his theory. But in 1915, he was finally able to publish his paper. And this is this paper. So this was called Die Feldgleichungen der Gravitation, which is German and says the field equations of gravitation. And this paper contained a profound insight, namely that gravity is not a force, but it is a consequence of the warping of space-time. And this is encompassed in the so-called Einstein equations, which relate the space-time geometry to the matter. So Einstein's equations establish a relationship between space-time geometry and matter, and they intimately relate them to one another so that one influences the other. So in fact, what happens is that large masses bend space-time, so they warp space-time. And in that bend space-time, other masses move on straightest possible paths. And there's a famous quote, which was coined by John Wheeler, which encompasses this. And the way he phrased this was that space-time tells matter how to move, and matter tells space-time how to curve. So space-time and matter are in constant interplay with one another and influence one another. So this is very, very striking, right? I mean, this is already kind of very shocking if one thinks about, if one was used to thinking about gravity in a different way. And now I want to also discuss what this means for time. So before, let me also emphasize this and say, okay, if we go to our picture that we had before, we had our falling elevator, and due to, if we now interpret this in Einstein's general relativity, you would say that objects in free fall follow straight paths in this warped geometry. So this falling elevator is just following the straightest possible path in this warped geometry. So now what happens to time in general relativity? So we already had kind of these weird effects in special relativity due to movement. However, you also have additional effects due to masses. And in fact, time slows down near very massive objects. So you have time dilation not only due to movement, but also due to large masses. And perhaps let me just state here, all these effects are really, all these effects have been measured with enormous precision. And they also find application in modern day devices, such as the global positioning system. So the GPS that we use in our phones when we open Google Maps to go from A to B relies on receiving signals from satellites to calculate the position. So it compares the times from different satellites to calculate where you are. And now, due to the weaker gravitational field in space, time moves faster on the satellites. And this time dilation has to be accounted for, otherwise GPS would not work. So the effects of special and general relativity actually also find application in modern day devices. Something which is extremely striking about general relativity is its predictions, because some would even say that general relativity has been the most successful theory of all time. So general relativity predicted gravitational waves, which are ripples in space-time which propagate at the speed of light. So here, actually, space-time itself is waving. And these ripples in space-time were predicted in 1916, so just 1 year after Einstein published his theory. And the first direct observation was performed by the LIGO collaboration in 2015. And later on, the Nobel Prize was given for their discovery. So this is a massive success of a theory if you predict something 100 years before. So if you predict something, it can be measured 100 years later. It's really extremely striking. Something which general relativity also predicted were black holes, which are objects which are so massive that not even light can escape the gravitational pull anymore beyond the event horizon. And these were also predicted just 1 year after Einstein published his theory of general relativity. And later on, after many, many years of evidence, which culminated in even having a picture of a black hole, the Nobel Prize was given in 2020 for their experimental verification. So now I want to talk a bit more about black holes because they're extremely interesting objects. So black holes arise at the end of a very massive star's lifetime from gravitational collapse. So due to fusion taking place in the core of a massive star, you have an effective outward pressure, but once a star has burned all its fuel, gravity keeps pulling it inward, and if a star is massive enough, then general relativity predicts that the star collapses until all the mass is concentrated in one point, which is the singularity, which is surrounded by an event horizon. So at that point, when you go closer to that point, the spacetime is extremely curved because the mass is concentrated there, and there actually the theory starts. There the theory breaks down. So at these singularities, you have a breakdown of our theoretical description, and this is at an extremely small scale, which is the Planck scale, which is 10 to the minus 35 meters, which is 20 powers smaller than the atomic nucleus. And we know that at this scale, we need a theory that unifies general relativity, so which describes large masses, and quantum physics, which describes phenomena at very small distances. And so we know that general relativity is not valid there anymore. And the expectation is that general relativity has to be replaced by a quantum theory of gravity. And this kind of brings us to today. So kind of the open questions today. And it's really extremely beautiful, this story of space and time, how it developed over history, I think. So how much our understanding has changed over the years. So if you think back in 1687, people thought that time and space was absolute. And then these experiments about light really started to change our perception. In particular, the Michelson-Morley experiment, which later showed that this medium that people had thought the ether did not exist, but which on the other hand always showed that the speed of light is always constant, no matter how you measure it and no matter of the movement. And this led to development later on of new theories, such as Einstein's theory of special relativity, and later on the general theory of relativity, which included the description of gravity. And this theory just 1 year later had these incredible predictions that we now know to be true. So this has been really a very interesting story. But now you might wonder, is there anything to do at this point if things have been so successful, and there are still many things to research if you're interested in gravitation. So one thing which definitely many people are grappling with are how to combine gravity with quantum mechanics into a theory of quantum gravity. So this is something many people are researching. And we don't know what is the right theory. There are many approaches, a very famous approach being string theory, but we don't know what is the right quantum gravity that describes our universe. Now, something which we are also still trying to understand just in Einstein's theory of gravity, so without going to quantum, it's the properties of solutions to general relativity. So in particular, you have solutions in general relativity which have weird behavior, such as loops, closed loops in time, where you could in principle go into the past. These are a priori allowed, but usually restricted because they are deemed unphysical. So something which people are still trying to understand are what are the solutions, what are all the solutions in the theory, what are their properties. Something which I'm very interested in are the properties of mass. So mass is a very interesting concept in general relativity, because space and time themselves have mass and not just the particles living in it. And that makes it kind of difficult to even define. And to define the mass, you actually need to single out a notion of time. So you kind of have to pick a time. I told you before, in general relativity, there are many times. And the notion of time that is typically picked is the notion with respect to a distant observer. And with regards to the mass of space-time, there are still many open questions. So people are trying to understand what are the properties of mass. In particular, can the mass be arbitrarily negative in certain situations? And it's not known for general spacetimes what are the properties of mass. So this is still very much an open subject in generality, even though for particular situations, many results are known. Here, let me end with some questions, in particular with regards to time. So, as I said, something which is definitely one of the largest open questions is what will be the right theory of quantum gravity that describes our universe? And it's also not clear what will be the role of time in quantum gravity. And if time is something which is truly something which we should truly regard as something fundamental or something which emerges. And with this, I would like to thank you all very much and hand it back to Sara.
Thanks so much. That was wonderful. So to our audience, there is a Q&A where you can enter your questions in the chat. We already have a few questions coming in that were sent ahead and also coming into the chat. So I'm going to start with some of the ones that we have already. Because I anticipate that you're going to get a lot of really great questions because that was such a wonderful talk. So we'll get straight to it. All right, the first one here is if causality were treated as fundamental, for example, as a second dimension of time, how would that affect general relativity's treatment of time and causality?
Yeah, this is a difficult question. So, because the way that causality is kind of in the theory, so it's not directly a new dimension. I mean, something one could ask what if there were two time dimensions, and for this is kind of the consequences would be quite drastic. So that would really, if one had two times instead of one time, that would really change everything. Yeah.
Great. We have a question from Barbara Temple, who's one of our regulars at Thinking Beyond. And she's got two really great questions. I'll start with one of them so we have time for others, and maybe we'll come back to the other one. But she's asking, what quite literally do you think time could be made of? As it stretches, what do you think might be stretching?
Yeah, it's all very interesting questions. So, so what time is made out of is very unclear. So I think people kind of speculate about, I mean, people try to understand this and have different approaches. So this is kind of also connected to what is quantum gravity and what will be time in quantum gravity. If it's really something to be regarded as fundamental, where you kind of quantize small units of time, or if this is kind of only a concept which kind of emerges from a more fundamental picture. So this is kind of a point where you can go very different directions, so to speak, right? You can treat it as something completely fundamental, or you can take this viewpoint that space and time will only emerge from something which is deeper and is completely different, and this is unknown. Yeah, it's very interesting. So I would like to know. It would be interesting if we could know in my lifetime. I'm not sure.
What makes it exciting, I suppose. That's why we're here, right?
Yeah.
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 Yeah, that's excellent. So I have a question from an anonymous attendee in our audience right now, and I'm going to ask this one ahead of some of the other ones because I think it'll be helpful for everyone. And the question is, can you explain relativity in simple words, as into an absolute beginner who doesn't know the basics?
Yeah, yeah. So I think yeah, it's all very good, very good question. Yeah, I think the thing which in relativity which is so very different is kind of that the time and space are connected. So you treat it as one when you are already in Einstein's theory of special relativity. So you cannot disentangle and just treat it completely separately. And that these two things will not be, that these two things are not things which are independently fixed, but what you actually fix is the speed of light. And because of this, the distances that you measure or the time that you observe as one observer are not absolute, but they are relative.
So we have many questions coming in. I think your talk's been very popular. This one comes from Howard. And Howard asked, does this mean that organisms on high gravity worlds experience time more slowly than on low gravity worlds? Would people on the moon mature slightly faster than on Earth, for instance? How big of a difference would it need?
Yeah. So in fact, yeah, this is true. So if you're near a larger mass, the time will go slower compared to someone which is in a lower gravitational field. So if you're like cannot be near the sun, but presume that you would survive being very near to the sun, you would your time would go slower compared to someone than on Earth. Yeah.
Can I just chip in? It's worth mentioning that, of course, this is easily measured with modern technology. The clocks are now so accurate that even lifting them in the lab is enough to show a change in, if you like, the rate of time or the rate the clocks go.
Yes. Excellent. So we have a question from Shashank, who asks, one of the simple definitions of time I read was the direction in which entropy always increases or stays the same. Does this still apply in general relativity?
Yeah, these are also very good questions. Yeah, so this is it actually brings in a point which I didn't mention in my talk, but something which is also a question which people are trying to understand both from a physical way or say in a philosophical way, is kind of that we have this direction of time, right? That you kind of in many different ways, right? In the way that our universe observed, or also when you think about entropy, that the entropy always increases, but it doesn't decrease, which was brought up in the question. But we have this directionality in time, which we observe in our universe. And this is kind of curious also with regards to the laws of physics, because most laws in physics are time symmetric. So you don't have a priori this directionality, but you obviously observe it in a way. Yeah.
Yeah, there's another question that's related, which is about what general relativity has to say about the arrow of time. This comes from James. So maybe you can elaborate a little bit more about whether it has anything to say or not on a directionality to time.
Yeah, this is a good question. I mean, a priori, you don't have in the theory built in a directionality. I mean, you can pick a directionality of time. But
Could I have a go at offering an answer to that?
yeah, of course, yeah.
So, as you point out, both in Newton's theory and in Einstein's theory, it's time symmetric, and so the laws themselves don't contain any error of time. But in the universe, we have to take into account the gravitational degrees of freedom as well as the matter degrees of freedom. And the universe started out very smooth. So adding to the entropy of matter, we have to take into account the entropy of the gravitational field. And so the initial conditions on the universe, or at least its early state, was such that the gravitational field was very smooth, and over time it's become more and more clumpy. And you were talking about black holes. That's an extreme example of the clumpiness of the gravitational field. So general relativity doesn't contain within itself a solution to the problem of the origin of time's arrow, but it tells us that we must formulate it by talking about the gravitational arrangement of matter in the early universe, and it was distributed very smoothly. The Big Bang coughed out matter and radiation distributed almost uniformly, and without that, we wouldn't be here now.
So another attendee asks, have you ever heard the phrase theory of everything? If so, can you give your insight on it?
Yeah, all the very very interesting question. Yeah, no. So this is I guess a thing which theoretical physicists are ultimately after, combining theories and ultimately having a theory of everything. So the issue right now is gravity, because we kind of can describe the other fundamental forces in the standard model, and we would describe them in the mathematical language of quantum field theories. So the important thing here is quantum. So these are all quantum theories, but right now we don't have a quantum theory of gravity that we know to describe our universe. And so the ultimate goal would be to kind of combine this theory of quantum gravity with the other forces in a theory that describes everything. That would be the dream, so to speak, of all physicists. Yeah.
Great. So we have a question about time is often described as the fourth dimension. If time's considered a dimension, why is it considered a dimension?
Yeah, absolutely. Yeah, so time, so in the framework of Einstein's special relativity, actually already, you combine space and time in space-time. So you treat time as a fourth dimension, but with certain so you include in the theory. So it's, time is, so you can still recognize that it's time due to the way you describe it mathematically, but it is a fourth dimension. So it's a special fourth dimension, but it is combined in space and time. So you have actually 4 dimensions, and this is how all these effects become much more clear actually when you describe them, right? If you see them on their own, if you see length contraction and time dilatation on their own, then a priori these things seem very wild. But when you describe them in space-time, it's much clearer how this comes about, so to speak.
Okay, our next question comes from an anonymous attendee. Why does general relativity break down when black holes come into the picture?
Yeah. So the reason why it breaks down when a black hole come into the picture is, at the very minimum, things break down at the singularity. So there we know that this is a problem just mathematically already, because you encounter infinities, which, yeah, so infinity is not a point. And so you already see there that mathematically there is something which goes wrong. And the reason why this is the case is because black holes are these extreme scenarios. That's also why people like them, because you have this prediction that the mass collapses from general relativity in just one point, and this point is of course highly irregular, and so you have these enormous masses which are concentrated in very, very small volumes, and so you kind of have to take both effects into account. So most of the time, either general relativity is important or quantum mechanics is important, and there are not so many situations where you really have to take both effects into account. And black holes are one of these scenarios where both effects become really relevant, and so none of the theories are working anymore at singularity.
Great. We have a question from Anand who asks, how do photons experience time?
How do photons experience time?
Suppose it depends on what you think experience is.
Yeah. Huh.
Could I answer that? Because it's often said that a photon is everywhere at once, and so it has no intrinsic time. But we can assign a number along a path that a photon might take. But if you were the photon yourself, you get from one place to another instantaneously in your frame. So I'm not sure that's very helpful because, as Sara says, what goes on in the mind of a photon? I think we don't know.
Yeah, it's a very human question to ask of a photon. We have a question from David who asks, Freeman Dyson seemed to be saying that the quest to have a quantum theory of gravity may be impossible or not verifiable. Can you explain this?
Yeah. I wonder what's the best way to, Yeah, I think it has to do with the question of whether gravitons would be really measurable. I'm not sure if Paul wants to comment on this, or
Yeah, maybe Paul actually knows why he said that since you knew him well.
Freeman knows him very well, and at the time he threw down this challenge. And I think you're right, Raphaela. It's in order to say that gravity is quantized, sooner or later you'd have to measure some effects that involve gravitation and quantum mechanics, such as detecting a graviton, which would play the role for gravity that the photon plays for electromagnetism. But because gravity is such a weak force, that seems a very, very difficult prospect. And you can put the numbers in and ask, well, how much would you have to get from the government to build a graviton detector, and how big would it be, and the size of the solar system or something? So it does look to be extremely difficult with standard sort of technology. But there are people, for example, there is the ideas of Frank Wilczek and his colleagues at ASU on the possibility of seeing some sort of pale shadow of quantum gravity effects at LIGO, the gravitational wave detector. So maybe indirect means. But at this time, you could declare that gravitation is not quantized, and there's no experimental evidence to show that it is. And the arguments that it should be are really entirely theoretical, something to do with the consistency of physics. But it may be that we've got it wrong. Maybe that gravity is ultimately a classical force or space-time field.
Yeah. I always find it interesting how the idea of unifying existing theories only became popular recently. And anyway, that's a whole nother thing about, physics generally. Okay. Colin has a question. How does dark matter fit into quantum gravity? And what would you say are the leading theories on this?
all very good questions. Yeah, so a priori, you don't really, dark matter has more to do with what we observe in our universe than directly with quantum gravity. So you can kind of phrase the question of quantum gravity very exactly, just from a theoretical perspective. So to a large degree, what people are right now trying to understand about quantum gravity is purely theoretical, in the sense that they're just trying to formulate one theory of quantum gravity, which is fully developed. Now, dark matter and also dark energy are things that we need to describe observations about our universe, but they are not a priori, I would say, connected to model candidates of quantum gravity, as far as I understand it.
Great. We have a question from Baldev about particles that go back in time. I guess the question is, are there such things, and can you say anything about them, or if they don't exist?
I mean, sometimes people just theoretically regard antiparticles as actually particles that move back in time. But a priori, we have an error of time, so things move forward in time.
But Raphaela, you did talk just very briefly about closed time-like loops, the possibility, not to do with antimatter, but the possibility of a particle that might loop back into its own past. And Einstein was always very worried about that. He thought this would be a disaster. And it's interesting that when he went to Princeton, one of his colleagues was the logician Kurt Gödel.
Yeah, absolutely.
Obviously, Gödel got interested in the general theory of relativity and produced a solution that does indeed enable an object to go from any point in space-time to any other point in space-time. It means that you could reach the past. It depended on having the universe rotating, which you might think is a bit artificial, but maybe it does, and it would show up observationally in the cosmic background heat radiation, the afterglow of the Big Bang. A rotation, if you measure that carefully enough, a rotation should show up. But Freeman Dyson told me that when he was in Princeton, he got to know Kurt Gödel very well. And Gödel took this very seriously, and he would phone Dyson from time to time saying, have they found it yet? Have they found it? Referring to the rotation of the universe. So he took it very seriously, the possibility of looping back into the past. He had that one solution. It's not the only solution, but mostly physicists don't like the idea because it creates some sort of causal chaos. And Hawking introduced the chronology protection hypothesis, the idea that this should be ruled out for some reason. But we don't have a theorem of that, do we? Nobody has proved.
Yeah. No, it's a very good point. Yeah, no, you're absolutely right. I think, yeah, it's always kind of a bit ugly if one restricts a theory by hand, so to speak. These solutions are absolutely there. You just usually don't consider them because they're unphysical. But of course, it would be nice to have deeper reasoning, so to speak, to either exclude them or.
It's an open question for any students listening now that want to go into this area. The other one is, of course, naked singularities. You talked about black holes, and part of the reason that we think there's need for new physics is that the center of a black hole would be a space-time singularity, whatever that is, and would suggest something new. But so long as it's inside a black hole, we don't stress too much about it. But if the black hole horizon were to disappear and the singularity would be exposed to our view, so to speak, then again, many physicists would think that that is a disaster and that we need to have a theorem that rules out naked singularity. Roger Penrose called this the cosmic censorship hypothesis. So we've got chronology protection hypothesis, cosmic censorship hypothesis. Both are still open questions. They may be connected, for all I know, but this is unfinished business. Needs to go on your list.
Why it's exciting times. That's great. So we have a few more questions coming in. I want to make sure I get Murtika's question in before the end because it's probably useful to other people. But the question is, do you recommend any books to read that explain the theory of relativity in simple words for people?
Yeah, no, that's a great question. I know Paul has written several books, so I think what would you recommend to start with, Paul, from your books, perhaps?
Obviously, I wrote a book many years ago, 1995, actually, called About Time. And so that dwells especially on the nature of time in physics generally, but also general relativity. And another one called The Edge of Infinity, which is a sort of weird title. And that's all about black holes, naked singularities, and wormholes and so on. So there's a couple. But of course, there are many other good books on the market. Don't read Einstein's book. That was pretty terrible, I found. I think this is a subject that you've been talking about, as you explained to us. It's been around for 100 years, over 100 years. And so there are many attempts over those years to put these somewhat strange ideas into simple language. My final feeling is that, Raphaela, it would be ideal if you wrote a book on this subject. That could be our next project.
There you go. Great. So we have a few more questions. We're almost out of time, so I probably have only time to ask you one or two more. This one also comes from Barbara Temple, and she asks, what would you say is the biggest obstacle related to time with merging Einsteinian relativity and quantum mechanics?
Yeah, also a great question. I think, yeah, that there's really much one could say about this. So for one, is kind of already that kind of the role of time is a bit unclear. There's one thing I said somehow in quantum mechanics, you kind of you don't quantize time, but then you have space and time, and you want to quantize the theory itself. You kind of have to think about how to treat time in that language. So it's kind of already a very fundamental decision there, and then kind of gravity just behaves very different from the other forces that we know, and one way to understand it perhaps is kind of that usually the way we did it with other forces is that we quantized things on a fixed background, whereas in gravity we know kind of that the background itself, right, is the fundamental thing, and then you kind of have to, instead of quantizing something on a fixed setting, you kind of go a level deeper, so to speak, right? You kind of try to quantize what is in the setting, so to speak. So it's just extremely different than other theories, and that's what makes it so hard.
Yeah. So we just have 2 minutes left. I'm going to take this sort of like host advantage to ask a question. But my question is actually on behalf of the audience, because I think we have a lot of people that are really enthusiastic and looking at someone like you as a role model, getting into this very exciting area of research. Do you have any advice for listeners out there that maybe are very excited about this area of physics, but don't know how to start thinking about it? We had a couple book recommendations, some excellent advice from Paul, but I'm just wondering, because you're, starting out on your fabulous career working in this area and making waves with your research, what advice do you have for people?
Yeah, I think nowadays the nice thing is that there are really like great resources online. You can you can kind of there are great explanations on the various channels on YouTube, in books. And I think also if you ask researchers, most people are always very happy and excited to talk about their research. I think, yeah, I think if one has excitement, one should just kind of go after it, because somehow this is, I think, the things that keep you going in your quest for understanding, so to speak.
Well, that's always excellent advice. Thank you so much for joining us for tonight, and for the lovely talk and all the questions you've answered. And to our audience, thank you so much for joining us this evening. Next month, we will have Phil T talking about the perils and promise of AI. So you'll want to join us for that. And we will see you all in a month. Thank you again.
Thank you too. Thank you.
Okay. Goodbye.
Bye, everyone.
Bye.